Let's talk about Chapter 1, the history of metallurgy. So metallurgy has a major impact in civilization. If you've studied history or just heard common terminology, you know that human technology is often described in terms of the best material available. So the Stone Age, the Bronze Age, and the Iron Age are typical terms people use to describe this. So in this class, we're going to look at some of these metals and how they've changed our society. So let me give you a few examples of how metals affect society. The first humans used stone. So stone makes a nice weapon. It's somewhat easily shaped, but it's very, very brittle, and it's difficult to shape into many useful objects. So things like plows are more difficult to make out of stone. Copper and then bronze were innovations that allowed more elaborate and useful tools to be made. The advent of high-performance nickel alloys allows the building of gas turbines, also known as jet engines. Without these high-performance alloys that can operate at high temperatures for extremely long periods of time, it's possible that jet engines could be made and used, but they would not be as efficient and produce the amount of power per unit of fuel they consume. And then the advent of cheap, high-quality steel at the end of the 1800s, which we'll talk a little bit about, allowed the proliferation of bridges and railroads that you can still see around today. And this couldn't be done without being able to make these materials in large quantities. The first metals available to mankind were those that were easy to find and easy to work with. So there's only a few metals available in pure form from the ground. Most metals are bound up in ore, which is just metals mixed with rocks. So the first pure metals were copper, which can easily be found in the ground. You can kick over a rock in certain parts of the world and find pure copper in its original form. You can hammer it, shape it, melt it, do a lot of useful things with it. The same goes for gold. Gold is highly prized because it rarely or never tarnishes. So it's useful for things like circuitry, electronics, and of course, jewelry. Silver can be found in its pure form. And interestingly enough, iron can be found in pure form, but typically, usually only as meteoric iron. So things that meteorites that come down, fall on the ground, and they just happen to be pure iron. We'll talk a little bit about this, but this was obviously prized by civilizations that only had copper or bronze. Another civilization, another tribe might find a big chunk of iron, be able to shape it into useful tools, typically things like fish hooks and knives. So pure metals are typically somewhat weak. So copper is very useful. It has a lot of good properties, but it's not very strong, and it can't hold a very good edge because of its lack of strength. The same goes for something like tin, which can be found in the ground, not very strong. Early man figured out around the time of the Bronze Age that if you take pure copper and pure tin and mix them together, you'll form a material that is stronger than either of them separately. Okay, so bronze, a combination of mostly copper with some tin, is stronger than copper or tin. It can be shaped, it can be cast, it can be used for things like plows, weapons, all sorts of implements. So this was a major technological innovation, and the process used to do this is called alloying. So an alloy is a combination of two or more metals together to form something more useful to us. Smelting is the process of reducing ore, which again is just metal mixed with rock, into pure metal. Some metals are much easier than others. So it's pretty easy to get copper out of ore, but it's very difficult to get aluminum out of ore. The technique to get aluminum out of ore was only really made economical in the late 1800s, which we'll talk about the process of how that is done. But before then, aluminum was extremely expensive to produce. So we talked about the Stone Age, which led to the Bronze Age, which of course was going to lead us to the Iron Age. So the Iron Age is when things really took off. The reason being that iron is very strong, it's very shapeable in the wrought condition, and it's plentiful in the earth. So it's quite a trick for early man to make iron useful. So iron melts at a much higher temperature than copper, bronze, or any other metal known in that time period. What essentially has to happen for iron to be worked back then was to take iron and charcoal and limestone, put it in a fire, heat it up until it became kind of like a spongy mass. The spongy mass would be partially metal and partially slag. So slag is a combination of things that collect. They're kind of the remnants of the ore. So what would go on here is you'd have this big lump of kind of looked like a piece of coal, right? It'd be iron with this slag, which is just the melted rock. And they would have to hammer it out, mechanically. So take this thing out of the fire and then just beat on it with a hammer until you got all of the slag, the excess rock, out of it. At that point, you would have a piece of what is known as wrought iron. Wrought iron is very, very low in carbon. We'll talk a lot about this in the semester. It's very malleable, but not particularly strong compared to steels, which have some iron, and cast irons, which have steels which have some carbon, and cast irons which have a lot of carbon. This resulting chunk of wrought iron were known as blooms. Early steel production was really a mystery until about the 1800s. It could be done, but they didn't have the science behind them to back it up. In India, they figured out something called the crucible method, in which they would just take this wrought iron and pieces of charcoal and encase it in a little tomb of clay and put it in a fire for hours or days until that charcoal would dissipate into the metal, producing a steel. The details don't matter too much, or the takeaway is that steel could be made in small quantities even before the Middle Ages. The steel is highly prized around the world if anybody could get it, but there wasn't really enough around to use for farm implements or building an Eiffel Tower or something. There's very little of it typically used for weapons. Cast iron was figured out in the Middle Ages. The big technology hurdle to create cast iron was the temperature of the furnace. So it had to be over 2,000 degrees to melt this iron, limestone, and charcoal in order to get it to be in the molten state. The way they did this with the furnace is by using a bellows, which just forces air into the chemical reaction, created more heat. So essentially you'd have a vessel, you'd put iron, charcoal, limestone, get it as hot as you can, pump air in there, which would accelerate the reaction. And inside of that vessel, the bottom would become molten, whereas the top would just be waiting to get into the reaction. So at a certain point, they would decide they wanted all the molten iron in the vessel, and they would do something called tapping it, which just means drilling a hole in the bottom of the vessel and letting the cast iron pour out. So in the early days, they would use a big bed of sand to let the cast iron flow into, and they dig little troughs of whatever shapes they wanted. So the liquid iron would flow through the sand trough into whatever shape they wanted, wait for it to cool down, they could pull it out and break off the runners that connect the troughs. Cast iron It's typically 2 to 6% carbon. It's very brittle, much more brittle than steel or wrought iron. Its strength is typically about the same or even a little less than steel, depending on the composition. Where cast iron really shines is its castability. It flows into molds extremely well, much better than steel, and its compression strength. So cast iron is still used for a lot of things today. So certain pumps and machine housings and frames are still made out of cast iron because they have great compression qualities and they can be poured into complicated shapes. So all the stuff we've talked about so far has been possible in the times they were made, so let's say before the 1800s, but they were really only possible in small quantities, not enough to build a Brooklyn Bridge or an Eiffel Tower. The Industrial Revolution, the development of steam engines, really necessitated more of this wrought iron, steel, and cast iron, along with things like copper. So when they're running telegraph cables across the Atlantic Ocean, they need a lot of very pure copper to carry electrical current. So this created the need for new processes to make metals. So the metals themselves haven't really changed a lot, but the techniques used to process them changed a lot in this period. So there's a couple new techniques. The first we'll talk about is called puddle iron. So the problem with wrought iron, as we talked about before, is it's got to be hammered. It takes a lot of physical effort to hammer out the slag from the iron. Puddle iron uses a very special furnace. There's going to be a picture in your textbook, but what it does is has a pool full of molten iron, and it blows air over the top. So what this air does is steals the carbon from whatever it touches. So in this case, the top portion of the pool of iron. When you reduce the carbon content of iron, it increases the melting temperature. So what this in effect does, if you have a molten pool of iron, but the top bit has had carbon taken away the carbon increases the melting temperature. So what happens in puddle iron is as you remove the carbon, the resulting effect will be a mass of low carbon iron that can be scooped out, kind of like an ice cube. So I made a quick graph. You can pause on this to take a closer look. But essentially what you have here is carbon from left to right, temperature from top to bottom. If you start over here with liquid iron with lots of carbon, and you move over to the other side, you have solid iron as the carbon goes down. So this line right here is just empirical. The green line is just what happens when you reduce or increase the amount of carbon. So we'll talk a lot about charts like this. This is just something I drew up. It's a small representation of the iron carbon diagram. So with puddle iron, they scoop this stuff out. It's already wrought iron with very little carbon, and it can be shaped without having to hammer out the slag. So this was big. This allowed people to make, especially in England and Europe, to make huge quantities of wrought iron. So this is what the Eiffel Tower is made entirely of. Wrought iron using the puddle furnace technology. So wrought iron, again, not particularly strong. It's very ductile. It still has its uses today, although mostly low carbon steel has taken that over. The next technology is the Bessemer converter. So this was in the middle 1800s. This is it looks like a big a milk jug on a giant trunnion. Okay, so the idea is you heat up all this iron and you blow air through the bottom. What this air does is strip the excess carbon out of that iron. So it does it very quickly, within maybe an hour or so. And then it's tilted over. There's some good pictures in your book. And the iron, the pure iron, is poured out. So this gets you wrought iron. The way steel is made is they would remove all the carbon from the unpurified iron and then add the carbon back in to get the composition they want. It's just easier to control that way. This reduced steel prices dramatically. So this made railroads, bridges, all sorts of things possible, locomotives that just weren't available at scale before. The next process is something called the open hearth. So these things came out about the same time as the Bessemer converter. They're still used today, but they produce steel much more slowly. So the idea of the open hearth is you put the iron in what's essentially a giant swimming pool. You keep it molten and you can add and remove the components of the alloy you want. So this is common in making things like tool steel that have to be very, very precise in the amounts of the different alloys that are added. So open hearth might take 8-10 hours to make what's called a heat. A heat is just all the steel that comes from one particular process at a time. In the late 1800s, the Hall-Héroult process, developed in France, was first used to produce aluminum. So aluminum doesn't work exactly like steel. You can't just heat up the rocks and have metal come out. Aluminum, the early processes used electrolysis. They'd pump DC current in to electrolytically separate the aluminum from the ore. It's still used today. Aluminum is very electricity intensive to produce. So a lot of times it's produced in places where electricity is really cheap. So near hydroelectric dams and places like Canada, right? France still has a pretty big part of the aluminum market, but they had it cornered, about 100 years ago. They were the primary producers of aluminum. So this process in the late 1800s, the Hall-Héroult process, dropped aluminum prices 90%. So it really made aluminum available to be developed into different alloys. Duraluminum was invented in Germany in around the 1920s and was used in airplanes extensively. And there's variants of it that are still used today. In the 20th century, there were several developments critical to steel production. The first of which is the integrated mill. So this was a phenomenon in the United States where you had these gigantic mills that had a blast furnace and a steel production facility. So Bessemer furnaces or open hearths or both. They could produce hundreds of tons of steel in a day. I mean, just huge economies of scale that made steel production very, very cheap. So in the United States, they got coal from the upper Midwest. So there's a huge range in Minnesota called the Mesabi Range. That's just a giant mountain filled with iron. And it's still where we get a lot of iron today. Metallurgical grade coal, so very pure coal called coke, came from Appalachia, the coal mines, some of them still run today, and limestone from the north central Midwest. These are the three ingredients used in the blast furnace. The next big technology was the basic oxygen furnace. So this was developed in Austria in 1952. One of the reasons is because basically all of Europe's industry was completely destroyed and they had to build everything from scratch. Whereas we, in the United States, already had integrated steel mills using processes that had worked for 50, 70 years. They were great. No need to, I won't say make improvements, but no need to rewrite the book on how to make steel. Well, in Europe, they had an idea. What if you just took a Bessemer converter and instead of using air to pump through it to get the carbon out, what if you used pure oxygen? Okay, so oxygen does the same thing air does, but a whole lot faster. So what they discovered They basically just took a Bessemer rig set up, just pumped oxygen through it, and they could get a batch of steel, very high quality steel, in about 20 minutes. So we're talking, 100 tons of steel in 20 minutes. So this process is very popular today. Basic oxygen furnaces are used extensively for making new steel products. The next big process is continuous casting. These old processes, so Bessemer, open hearth, and basic oxygen furnace, they typically would, have this giant ladle full of metal, pour it out, send it to a yard, and pour it into giant things called ingots. These ingots were just a good place to store the metal until they went to the mill to be rolled and hammered into useful shapes. The continuous casting operation takes the molten pure steel and pours it down this long thing that looks like a slide, right? And it's continuous. And it creates very dimensionally accurate slabs of metal and somewhat useful shapes. It's a process used extensively today. It was first developed around the 1960s. Almost all new steel is done with the continuous casting process. The next technology, the electric arc furnace, uses electricity to create the heat to melt the metal. So these are extremely popular for scrap metal. So there's things called mini mills that started popping up around the United States in the 1970s-ish. What they would do is have a somewhat small operation, so not hundreds of tons, maybe dozens of tons, and they would take scrap metal from cars or rail cars or railroad tracks, whatever. They'd throw it in a big pot with these huge graphite electrodes, run electricity through it until it got molten, and at that point, they could have a lab to check the composition. And if they needed to, they could throw in a bag of charcoal for carbon, or they could throw in manganese or whatever they needed to get the composition correct, and then pour it out into useful shapes. So a huge percentage of steel in the United States today is made with the electric arc furnace. The reason being, there's not a demand for brand new steel that has to go through a blast furnace, that gets mined, blast furnace, continuous casting. You can typically find scrap steel, remelt it and get the composition right and use that as new steel, because there's so much steel around that gets recycled. The next big development that's coming online is called direct reduction. So in the old way, with the blast furnace, you'd have this huge facility with this giant chimney-looking thing. You'd have to pour limestone, coke, and iron in it in alternating layers, and then blow blazing hot air through it to get the reaction going, and that would produce your molten steel, okay? That's a very expensive, complicated process, and these giant blast furnaces have to run 24/7, 365. You can basically never turn them off without costing millions and millions of dollars. They're very difficult to turn on and off. Direct reduction eliminates that. It's just going to take iron ore and then use a combination of methane, hydrogen, and carbon monoxide to remove the oxygen from the iron. And this also removes any, contaminants in there. It essentially takes iron oxide and makes it into pure iron, okay? This process isn't too widespread yet, but it's the next technological development that will probably take over eventually.